know what these things look like, now we got to deal with what can we do with these? How does your body deal with these things so that it can turn these wonderful nutrients into energy? Okay, so that's what we got to do: how to transport it into your bloodstream. So we're going to show you first proteins, how we digest and absorb proteins, and then how do we digest and absorb carbohydrates, and then the tough one for most students is going to be how do we digest and absorb fats and lipids. So we'll save that for last. So the major thing here is that you have to break things up into its simplest components. Okay? Sorry about that. So, digestion of proteins. So we got to break things down into the smallest components first. Then they can get absorbed. You can't have proteins get absorbed into the bloodstream. They're just too damn big. We have to break them down into amino acids. Okay? So that's what's going to happen. It must be broken down to amino acids first, and we have enzymes that will do that. But I also want to note here that sometimes if we have, let's say, if this is a protein, which is all a long chain of amino acids, and they could be very, very long. They could be like 300 amino acids long. They need to be broken down into amino acids, single amino acids, for it to get in the bloodstream. But sometimes, if they're small things, like maybe 3 come together, they could be small enough that they can get absorbed too. Now, when they're amino acids, your immune system doesn't recognize it as anything bad. And they're so small. And they can't be recognized. They're not immunogenic. But when they have something where it's a little bit bigger and can get absorbed, they can be big enough that your immune system can decipher that that's a foreign thing. And this could get absorbed into your bloodstream. These single amino acids could too. Now, most people, even if they come as, let's say, 3 or 4 amino acids, and they get absorbed in your body, they usually don't pose any problems. They get absorbed in your body, and there are other things that can break them down, and you can do whatever. But certain people might see this as a problem. And this is how you can explain shrimp allergies and peanut allergies. Because some of these are big enough that can set off a chain of reactions, as you see in the immune system, and cause an anaphylactic shock. It seizes a foreign body, attacks it, and it starts off your whole body into an anaphylactic shock. So I mention that mainly just to explain to you, they usually break down into just one amino acid, just a single amino acid. They can be broken down into, let's say, still small, 3 or 4 things, and your body can see that it's foreign and cause a chain reaction to it, immune reaction. And that's how you could explain what food allergies are all about. Does that make sense? Okay? So that's what that is. Now, you'll see this picture quite often. I just want to show you how to read it. Basically, you have the mouth over here. Here's the stomach. This is going to be your small intestines. And things come out of the pancreas. Now, our goal is to get proteins and put it into our bloodstream. So here's the major components that are going to be needed for breakdown of proteins and absorption of proteins. In the mouth, nothing happens. There's no absorption, there's no digestion of proteins going on in the mouth. In the stomach, that's where protein digestion begins. There's going to be an enzyme that comes out of the stomach called pepsin that is going to start breaking down the proteins into smaller units. Okay? Then we're also going to have, when it gets into the intestines, the pancreas is going to bring out a slew of other enzymes to help break those smaller peptides, or those smaller, a little bit bigger than this, but smaller chains of amino acids, and break them down into, let's say, dipeptides or tripeptides until they get to smaller products, until we can get them into amino acids. Amino acids can now easily get into the bloodstream of the small intestines. They're so small they can get absorbed in there. With an occasional 2 or 3 different ones like this that can get in there too, that can cause some problems. Okay? Questions about how to read that? All right? All right. Now let's talk about digestion and absorption of carbohydrates. Okay? Again, you've got to get it into the simplest forms, the monosaccharides. Disaccharides, and let alone polysaccharides, there's no way those can get absorbed. They're just too damn big. So we have to break them down. Starches have to be broken down. Remember, starches are polysaccharides, long chains and branches of these monosaccharides. Amylose is a type of starch, and also glycogen is. These are just polymers of glucose. You got to get them down to smaller sections. Disaccharides, so we have enzymes that can break down polysaccharides into disaccharides. I'll show you that. Disaccharides, we showed these earlier. But then you can have the absorption, and it must be broken down to the smallest form. Okay? So here's a polysaccharide, a starch, long chains of glucose. Okay? You can't absorb that. So we have amylase. Remember, it ends with an ASC. It's an enzyme. Amylase will break down this starch. Now we have salivary amylase, so carbohydrate digestion begins in the mouth, as opposed to protein digestion begins in the stomach. Amylase is going to come out. We have salivary amylase. It's going to break down the starch that's in your mouth that you're eating, crackers or whatever that is. Now we also have another amylase that's from the pancreas. Now why do we have salivary amylase and we have pancreatic amylase? Well, if you eat like me, I bite and swallow, so it doesn't stay in my mouth for very long, so I better have another source of amylase to break down my hot dogs and stuff like that, my bread, you know what I'm saying? So even though it starts in the mouth, it's not very efficient unless you're going to keep the food in your mouth like some babies do. It's not gum, but they keep it in their mouth, so they break it down more in their mouth. Okay? Then you break it down into disaccharides. These are called maltose. Maltose, which is 2 sugars over here, disaccharides, gets broken down by maltase. Maltase is a pancreatic enzyme. So these can be broken down into the single forms of glucose. Does that make sense? All right? Pretty straightforward. Again, when you get to the glucose level, the monosaccharide level, these are the ones that can go right into our bloodstream. All right? Again, what's happening over here, you saw this before, you have here one ring, and here's another ring. If we add water, if we remove water, it's going to make them 2. So you have 2 sugars over here become 1. But what we're going to do with digestion is the opposite. We're going to take this maltose, and if we add water to it, then it breaks up into 1 sugar here and 1 sugar here, monosaccharide. All right, that's just digestion. Digestion goes from disaccharide to 2 monosaccharides. And what's happening here, when you look at a schematic view, you got the starches. The thing Tylen is this P-T-Y-A-L-I-N. You see this word often in the textbooks and in my PowerPoint presentations. That's just another fancy word for saying salivary amylase. Salivary amylase and Tylen are the same thing. You also have pancreatic amylase that just comes from the pancreas. But either or, the starches, which are long chains of polysaccharides, they're going to be broken down into disaccharides. They can turn into lactose, maltose, and sucrose. These are disaccharides. The pancreas is going to spit out sucrase, maltase, and lactase. And those disaccharides will turn into monosaccharides. Now it can get absorbed into the small intestines and then eventually into the bloodstream to go to the liver with this hepatic portal system. Okay? Questions on that? Pretty straightforward. When you take this picture here, again, you have there's the carbohydrates. In the mouth, you're going to have some of these salivary amylase is going to start breaking down some of these carbohydrates. Nothing happens in the stomach except just churning. There's no chemical digestion going in the stomach. But in the small intestines, which is all this yellow, sure, the pancreas is going to spit out a whole slew of different enzymes to break down those disaccharides or polysaccharides into their smaller components as monosaccharides, so lactose, fructose, and glucose. This can now get into the bloodstream. Okay? Questions on that? There are certain polysaccharides are indigestible. They get the cellulose, and that just goes out your poop scoop, right? Roughly aged in fibers. Okay, now the big one, fats. Okay, so what's happening with fats? How to break this up? We have to talk about what emulsification is. Okay? Emulsifying is just being able to create a higher amount, of surface area so that lipase can actually break this up. So what this is if this is a fat droplet here, the only place that lipase can actually attach, and again, lipase is an enzyme that's going to break down fat. The only places that we can actually have lipase work on is the surface area that's exposed to it. So what emulsification is, we're going to learn from the liver. The liver is going to produce bile salt that is able to take this fat droplet and break it up. So this is going to turn into, let's say, 2 pieces. I'm just exaggerating it. So the original place that lipase can hit is right here. But we now created 2 new surface areas. We have a new surface area over here that lipase can also get to, and a new area over here that lipase can go to. And bile salts will emulsify this even further. I'm not going to really draw it for you, but you'll get the picture. It turns into a structure here, a structure here, a structure here, a structure here. So we can actually increase the surface area so that lipase has more surface area to attack, right? We can take this structure here. The only place surface area can actually, lipase can actually go is all over here. But if I break it up into 2 spots, or 1 spot, I now have 2 new surface areas where this is. So now lipase can go here. So understand what surface area is. It's the place where things can be exposed to on a structure. All right? So that's what's going on with this. All right? So we have enzymes to start breaking down these lipids, and they're pretty straightforward over here, right? These are lipase over there. Now, that's what's happening in small intestines, all right, in the lumen of the small intestines. But we're not done there. We now have to get them absorbed into the cell of the small intestine, okay? When that happens, it's kind of difficult to do that. So we've got to have these new transportation routes. You see, if you want to cross the Hudson River from New Jersey to New York, you can't very well go across that river nicely. You've got to be put in like a submarine and then go in there, go across the Delaware River, and then you appear on the other side. Same way here. Those particles that we just broke up into, those smaller lipid particles, can't get absorbed in the blood. Can't get absorbed into the cell of the small intestine. So we have something called micelles. Micelles are little transport things that take all the bile salts and all these products that you just broke down the lipids into, and now they go into this little submarine that can cross and get into the cell of the small intestines. Because on the other side of that cell is the bloodstream. So that's what's going to happen. We're going to have this little carrier, tiny little carrier vehicles to get that in there. All right? Now, when it does, like I said, bile salts are these amphoteric structures, which means part of it likes water and part of it doesn't like water. All right? The polar ends. It makes it, the micelles, to be soluble in the chyme. Okay? We're not water soluble in the water of the Hudson River, but the submarine kind of makes us soluble in there. Does that make sense? So these are little carriers so that all that stuff is actually, you mix water and oil, it separates, right? It's not water soluble. So that's what's going on with this. So this is, forget about what this is and this for the time being, but that's what a micelle is. A micelle is these bile salts, and it's these little holes, these little lollipop-like things are phospholipids, but they're bile salts. And inside there, we could put anything inside, and it will make this whole thing soluble in that fluid, so that it can get into the cell of the small intestine. You could put fatty acids in there, you could put glycerol in there, you could put puppy dogs in there, you could put anything you want in there. It's going to be able to cross and get into the small intestine cell. That's what a micelle does. It makes it soluble to get into there. Now, once it gets in there, inside the small intestine cell, the lipid particles that we just broke up get recombined. And they go back to that form. I got pictures to show you this. It goes back to the forms of what they originally were. Okay? Some things called apoproteins are added, and they get activated when combined with these products. Okay? And what happens is they're called chylomicrons. They're found inside the small intestines, and these chylomicrons are now too big to enter the bloodstream. So we have another problem. We need to get it into the bloodstream to get into the liver and stuff. So they're just too big to do that. So we have to have another way to get them there. That's where we have modified lymphatics that can take on these bigger structures. They're called lacteals. I know it sounds very peculiar because you hear lacteals, you think of lactose, you think of prolactin, you think of milk. That has nothing, lacteals have nothing to do with milk. Be careful with that, hint, okay? But these are modified lymphatics. They're just too big to enter the blood system, the portal system. So, not the lacteals, but the products, the actual products. So they have to go through these lacteals to get there, okay? And just as a side note, I just want to mention that there are certain small fatty acids that are able to slip on in and get into the bloodstream, but it's not a whole lot. Most of, and that's what you need to know, most, if not all of the fats that you eat have to go through the lacteals to get back into the bloodstream. They can't directly get into the bloodstream. So this is a little cartoon kind of thing I kind of saw, and I kind of broke it up for you. But you have this large triglyceride fatty lipid, and we got to break that up. So we're going to add bile salts to break them down into something like this, so that it increases the surface area. This is called emulsification. You're emulsifying the fats, you're breaking them down into smaller products so that you're increasing surface area. That's what it means to emulsify fats. Okay? Then you're going to have the pancreatic lipase come out, and it's going to break it down even further so that we can actually do something with it. Okay? They go into these micelles that are these transport mechanisms so they can get inside the cells of the small intestines. When they're inside the small intestines, the apoproteins get added to this, and they reconform back to what they originally were. All right, so they're back formed into a triglyceride, and then when this happens on the back end of the small intestines, they're now known as chylomicrons, and they can enter. They're too big to enter the blood vessels, so they enter the lacteals. So here's the lacteal over here. Here's the blood vessel. It enters the lacteal, not the blood vessel. Okay? A little bit more complicated than the proteins and the carbohydrates. You can do the same thing over here, understanding all that. Remember, it doesn't go into the capillary, they go into the lacteals. Okay? Again, showing this whole thing in a cartoon form. You got triglycerides, esters, phospholipids. They need to be broken down, so they're going to be broken down by lipases, esterases. Once you have the bile salts over there, and they'll be broken down to FFA as free fatty acids. They turn the bile salts go in here, and then you got this micelle. The micelle is going to have all these pieces all over here, plus the bile salts, and now this can get absorbed into our small intestine. When it gets inside the cell of the small intestines, apoproteins are added to this, and these things are reconformed to what they originally were. They're just too big to enter the capillaries, so now they go into the lymphatics called the lacteals as chylomicrons. Okay? Busy, I realize. Okay, this is the tough one. Okay? So, when you look at this picture over here, where's all this happening? Okay. In the mouth, nothing really happens in the mouth. Okay? So what's going to happen over here is that the triglycerides. Well, there is, I'll be honest with you, in the mouth there is lingual lipase there. So as much as we saw salivary amylase for the carbohydrates, there is a little bit of lipase in the mouth. It's not very efficient, but it does start the lipid breakdown does start a little bit in the mouth, but it's not very efficient. So you have some of that happening in the mouth. In the stomach, there really is nothing happening in the stomach except for the churning, the mechanical digestion. But there's no chemical digestion of fats happening in the stomach. It's really all happening in the small intestines over here. The liver will give you the bile salts, the pancreas will give you the lipase. You start breaking them down, they'll reconform, they'll get into the cell of the small intestines. And as chylomicrons, they're going to enter the lymphatics, which is the lacteals. Later on, further down the road, they go into the bloodstream. Okay? Questions on that? All right. So this is where it's. You can do this on your own, but it's showing carbohydrate. Here's the mouth, stomach, duodenum, or you can say that's the intestines, all over here. You can carbohydrates, proteins, lipids, and you should have an idea of where these digestive processes are all happening between the carbohydrates, proteins, and lipids. Okay? Questions on the exam on this, I guarantee you. Okay, but you'll see them in the review questions also. Okay? And then last I want to do on this is the lipoproteins, and then we'll get into the easier stuff. This is where LDLs and HDLs all come in. Okay? We have densities going on here. We have lipid, which is low density lipoproteins. I'm sorry, let me just repeat it. So lipids are low dense to water. In other words, if you put a drop of oil to water, it's going to float on the water. It's not as dense as water. It's floating. You know what I'm saying? It's less dense than water. Proteins, however, are very high dense, and they sink down to the bottom. Okay? And the chylomicrons that we talked about are extremely low dense, and they will be found on top of the lipids. So here's the key things I want you to understand with this, is that we have something called VLDLs. These are called very low dense lipoproteins. These are made in the liver, and they transport triglycerides to adipose tissue, to fat cells. These can be converted, this is the key thing here, these can be converted to something called LDLs. LDLs are low-dense lipoproteins. I know you guys heard of this, or you should have heard of this when dealing with cholesterol. Okay? But LDLs transport cholesterol. Now that might sound really, really nice, but the problem is they're scavengers, and they look throughout your whole body for cholesterol, but they take the cholesterol and they put it in places you don't want. They put it in the walls of your arteries. So it sounds like they're doing a good thing by taking it out of your body, but they're putting it in places you don't want. So LDLs are, if you have high levels of LDLs, you're at a higher risk of getting cardiovascular disease because it causes atherosclerosis. So very high levels of LDLs are bad for you. I sometimes call these the lousy cholesterols, right? L for lousy. These are not what you want high in your body. But we also have something called HDLs, high dense lipoproteins. Now these are also scavengers looking for cholesterol, and they look for the cholesterol, they grab it and collect it, and they put it in places you do want, namely the liver, because the liver knows exactly what to do with it. You'll either go out with your poop or pee, or make bile salts, or make steroids, make a lot of different things with it. So you want to put it into your liver. All right? So it transports the cholesterol into the liver, and these are what we call the better cholesterol. So if you have high cholesterol, that doesn't tell me anything. I need to know what's your number for LDLs versus HDLs. If you have high levels of HDLs, that's telling me that you have a good, this is actually going to be preventative of cardiovascular disease. High levels of HDL and low levels of LDLs is what you want. Okay? So HDLs, I just think of the healthy cholesterol or happy cholesterol. The LDLs are the lousy ones for the L. Okay? Questions on that? All right? And you could do this on your own in terms of HDLs or LDLs. And this is how it kind of gets, for LDLs, how it takes the cholesterol and it gets it absorbed into the walls of the artery.